Well, thank you for having us. And I'm going to follow up on Dan Miller's virtual watershed and talk in detail about how we've been working with folks in Alberta, Barry White and Chris Bader, John DeWoo, and Axel Anderson, among others, to try to bring in wet areas into some of the riparian tools that we've been building in the lower 48. We had a few projects in Alberta where we take the 1 meter LiDAR and the WAM and we integrate it with what Dan was referring to as a virtual watershed. And then our two focal points has been on looking at the riparian zone and its delineation and some various aspects of that, and as well as roads. And Dan just touched on that, and then tomorrow at another workshop, we'll talk about in more detail some of the road analysis we've been working on, as well as things involved with wildfire, which is a hot topic in the US. So the modules in NetMap cover fluvial processes, aquatic habitats, riparian, erosion and slope stability, Dan touched on that, roads, pipelines, wildfire, climate change, and today, this morning, we're going to talk about the riparian management component. So this is just of the module in the riparian zone, and this is a toolkit that sits in ArcMap. There's four major components. One is to delineate the riparian zone itself based on varying processes in it that we'll talk about this morning. And then there's in-stream recruitment, which can be done at the individual forest harvest scale, but also at the watershed scale for things involved with restoration, and then upslope sources of wood involved with mass wasting and landsliding. And then shade thermal energy is a big topic, both from protection from current forest, but also restoration where they've taken out old trees. And then thermal refugia is getting to be more important at the network scale because of climate change. What are the reasons for analysis and delineation of riparian zones? Obviously, forest management in general. People put them on to protect streams. And then also in the lower 48, because of the past history of timber harvest and so on, thinning is becoming an important issue. But it's a sensitive topic because it's a buffer zone. But some of these buffers are just surrounding second growth, dense forests that have been clear cut in the 1950s, 60s, 70s, and 80s before there was even stream protection. So people are arguing that they should go in and thin them, improve the forest health. But there are regulatory agencies that are worried about, well, if you go in there, what's going to happen to the shade, to the thermal energy into the stream, and to wood recruitment? Another reason is just restoration to improve currently degraded conditions along streams. Agricultural areas in the lower 48, for example, are pretty much given a pass. So most of the regulations are on the forest community. And then conservation in general to design functional riparian zones. So at least down where Dan and I hail from, fixed width buffers are pretty common because they're easy to implement and easy to check on by the regulatory agencies. And so you see a lot of this going on. And then, of course, as well as in lower gradient rivers. But as we all know, riparian zones are not one size. So there are the WAM is a good sort of indication of how variable things are out there. Very, very variable. And then floodplains, if we look at these different colors, which indicate different extents of the floodplain as you move out into lower frequency floods, it's very variable, right, from one spot to another. So people think about, at least in the academic literature, a functional ecosystem based on different kinds of processes. Wood recruitment is one zone. The thermal energy control by shade is another. The floodplain is another. The wet soils and wetlands is another zone. And there are others. And so back in the 1990s, when there was something called the Northwest Forest Plan, which was trying to save the remaining old growth in Washington and Oregon and Northern California, they said, how big do these areas have to be? And so they started building these curves called source distance curves. So this is the cumulative effectiveness, and this is in indexes of a tree height. So old growth trees might be 50 to 80 meters or something like that in terms of height. And so you can plot these based on the literature is what they did to try to get a sense where things were being controlled as you moved away from the stream. So if you think about riparian processes that can be evaluated in the context of a riparian zone, there's a whole suite of them. And so floodplains is obviously an important one. Wet soils and wetlands is another. Shade and thermal energy is another. Wood recruitment, this is a big deal in the lower 48. There's some listed species of salmon in low gradient streams like the coho salmon. And there's a large body of literature that says the wood in the stream is fundamentally important. And so you've got to have it in there. And before 1980, like between 1960 and 1980, they pulled it out of the stream because they thought it was something bad. So that's a good lesson about how wrong you can be. So for 20, 30 years, even the fishery agencies were yanking all the wood out. And then before that, some of the logging companies back in the early 1900s splash dammed, which means they ran log drives down the rivers, and of course they cleaned all the wood out. So that's a big deal, and thermal refugia is getting to be a topic important from climate change. So where are the areas where there will continue to be cool water as the temperature warms? Erosion potential along the stream can be encompassed in the riparian zone. And then tributary confluence areas can be considered as biological hotspots in many areas. And so these are all things. And you might be able to add to this list. So in the examples I'll be giving this morning, we're going to look at the Simonette River. We had a pilot study area of 4 LiDAR tiles. We've since mapped the entire Simonette, and now we're working in the Whitewood River Basin. And then the Nehalem River is in northwest Oregon. So I'll be moving back and forth between looking at a process of the riparian zone, how we map it in NetMap using the virtual watershed concept, and then some examples on, for example, forest management, how you might use it, or also restoration. And eventually, towards the end, talk about how to delineate a zone in the Simonette. So we have a method in NetMap to map floodplains, which is looking at the surface elevations of the near stream areas relative to the channel elevation. And that delineation is conditioned by the proximity of that land surface to the stream, as well as slope gradient next to the stream. And you create maps of surface elevation. So for example, this is in the Nehalem watershed, and this is the surface elevations, and you can see them here in terms of meters. And you can actually see, now this is 1 meter, 2 meter LiDAR. You can see the varying features that would be oxbow lakes, marshes, floodplains, and terraces. And you can see their corresponding mapping in this sort of agricultural area along the valley floor in Google Earth. But we often think of floodplains in terms of bankful depth. So if you take the elevation above the channel, you say, how many bankful depths is it? And that's a common geomorphic technique. And 2 or 3 bankful depth floodplains, that's also often considered the floodplain. And so in here in the Nehalem, you can see this is 1 times bankful, 3 is the green. Actually, 1 is the black, and then 2 and 3, red and green. And then blue and yellow would be considered high terraces that probably never get flooded. This is the Simonette. And look, it's very, very different because it's a very different landscape as people have been describing it this morning. It's much lower relief. And so you get a map that's really quite different than you would in sort of the uplands or the foot slopes of the Rocky Mountains. So what I wanted to explain here is interesting, and it might have relevance for Alberta. So what we have in the United States is called the FEMA flood maps, Federal Emergency Management Act And that's what these are, 100-year floodplains. This is the mouth of the Nehalem, so the Pacific is right here. And that's the gray. And then this is our NetMap tool that we ran in the same location. Of course, we get higher resolution because, well, we had LiDAR and they didn't, so that's unfair. But also, we also have ways to map different elevations of above the channel. And this is another example right along here, this kind of gray area, that's the FEMA, and then this is our mapping here. But the point I want to make is that there are holes. So the national flood mapping doesn't extend beyond urban areas. And so this is a problem because a lot of where we work and where the timber companies or the agencies worried about coho salmon or other fish species, they work all over these areas. And as you see from Washington State, only the urban areas are covered with these gray areas. The majority of the landscape does not have this data, this mapping. So it's like, how do you do it? So I don't know what the status is in Alberta for this kind of a problem, but that's something that we could discuss later. So another riparian process is the wet areas that you've been hearing about this morning, which is a great product. And so there was some discussion by Chris on how these actually maps are created, so I won't reproduce that here. And this is an example, right? This is an example that we saw before. This is, of course, in the area that we have been working in. And this is the wet areas, and the closer zones to the surface that are wet would be the warmer colors. But I wanted to show how this wet areas compares with our floodplain mapping in the Simonette. So there are places in the Simonette, a very diverse landscape, obviously. This is a relatively in size main stem stream, the Simonette River, and the wet areas are pretty similar in spatial extent to what we would consider a floodplain. But there are areas in the Simonette where our areas are less than the wet areas. So we would map a floodplain that would be narrower focused than the wet areas, which makes sense. You're just looking for the areas that would be inundated as the flow came up in a river system, and the wet areas goes beyond that because they're interested in just where the water is across the landscape in terms of the surface. It doesn't necessarily have to be adjacent to the stream. And then there are places where the wet areas is less than some of our predictions for the floodplain zone. So they're both very relevant attributes when you start thinking about riparian zones and streamside protection. Another process is shade thermal energy. And what's important there is just the physics of light transmission via the topography and streamside vegetation. Channel orientation is important, like which way the channel is pointing. And so you can see the different things that people use in their simulation models to think about what vegetation next to the stream does to the stream channel. So this is an example of what we refer to as bare earth radiation. This is in the Simonette. So imagine taking all the vegetation off the surface and then making the sunshine on it at some part of the day or some part of the month. And you end up with bare earth radiation in terms of watt hours per square meters. And look at just the role of aspect of the stream. If the stream is facing south, it gets a lot more sun, right? And if they're facing north, they get a lot less. And so you get that kind of spatial pattern, which you can think of in terms of sensitivity. For example, what if this watershed burned down and there was no vegetation left? Which streams are more likely to heat up? But we really want to think about shade. So we have vegetation next to the stream, and the shade model we use is sensitive to the height of the vegetation, obviously, but also how dense it is. So blackberry bushes right next to a stream is really effective, right? But they're really low to the ground, and so they don't shade hardly any amount of the stream itself. But these large old trees shade a lot, but they are less dense. They're less dense than a blackberry bush. And so between basal area and height, which is available in the data sets in Alberta, we can now start calculating the effect of shade, current conditions of shade in places like the Simonette. So this is a map that has the shade component. It actually has the vegetation height and the basal area, And this is in watt hours per square meters, and the warmer color means there are channels getting more radiation than those that are the cooler colors. So the interesting thing that we just sort of worked on recently, and maybe folks are aware of this, but we weren't, admittedly. But the effect of shade is very sensitive on which side of the stream you're on. Now, the funny thing is that does not really come into play in the regulatory communities. They say we want a 100-foot buffer or a 30-meter buffer, and it's same sides, both on same sides. And they don't think about this, but it really matters which side of the stream you're on. So from a fixed width buffer, which are these sort of dashed lines you can see, it's got equal distance on both sides. This is north, so that's north facing, that's south. And if you do in what we call an optimized buffer calculation, then you end up with the red. And you have much less need for a buffer on the north side. And we have a plot of that. Let me explain what this is. And I can't find this in the literature. That's probably somewhere, but we made this a few weeks ago because we were getting into this. And sorry, this axis is in feet because we were actually doing it for a private timber company in Washington. And this is channel azimuth from 0 to 360 degrees. So these color codes is the buffer width on the left side and the right side. But it depends on which side of the stream, which way you're pointing. So if you're pointing east, the left side's on the north. If you're pointing west, the left side is on the south. Okay? So the point is, in all this, is that it's extremely variable where the buffer width size, where it is relative to which way the stream is pointing, basically. So if you're going to design optimized buffers, then the tool needs to know which way the stream's pointing and what the width is. So that's like from a management perspective, if you were designing optimized buffer zones for forest management. But people are starting to think, wait a minute, people have been managing these watersheds for 100 years, and they've been cutting all the trees down, they've been putting agricultural lands, and now we have endangered species of coho salmon in the Nehalem watershed. Where do we add shade? So we can run the shade model that you saw before, but then that's the current shade, and then we go into the watershed and we say, well, what kind of vegetation can you grow here? What kind of vegetation could you grow in an agricultural area? What's the old growth vegetation like, or even mid-growth? And you run that tool, you run that analysis, and then you subtract that from the original or the current condition, and you get a map that says where you would get the biggest benefit if you could add shade. And the red areas and the yellow areas are the areas that you'd have the biggest effect. And you can see that graphically if you take that map and you overlay it on Google Earth. And so this is the lower Nehalem. This is all industrial forestry here. They all have to have riparian buffer zones, right? It's regulated. The agricultural people don't have to have anything. It's a sacred situation, but it's probably going to change because these are listed fish. And so what this map says is that if you're on a big river that's 100 meters wide, it doesn't matter putting trees next to it. It's not going to affect the thermal energy load because the channel's too wide. Most of the energy is coming right over with a 100-meter wide channel. It doesn't matter what your trees are doing. So don't waste your time. But these little channels here, right up these small ones, and they go up in industrial forest land, they're all red because they're 2 or 3 meters wide and there's blackberry bushes next to them. And by the way, these are the best coho rearing streams. So these areas would have the biggest effect if you were going to, from a restoration perspective, put on additional shade areas. Those would be the places to concentrate on. And so you can do this analysis because you have current current vegetation conditions, as we'll discuss this morning, even with LiDAR, and then you hypothesize a future ideal condition. Like where can I grow some big trees, basically? And then you get a calculation that would indicate where you might want to do some action. So that was restoration, and now we're going to think about forest management. And this is an issue that is getting to be very intense in the Northwest. I just came back from a American Fishery Society America meeting in Oregon. There was an entire session on thinning in riparian zones to reduce fire risk, but also because it's a dense second growth stand. And the fish biologists are saying, this is not good. You know, we need some light. We want to cut holes in the riparian zone. We want to add some wood. And, but you have NOAA fisheries, on the other hand, saying, hey, wait, that's dangerous, because if you even lose one stick of wood in this stream because you thinned it, then we're going to shut you down. So there's this battle. And so NOAA fisheries were at the meeting explaining their perspective. And then, of course, the timber industry was there, and the Forest Service was there. And so there were 15 talks on this. So we're going to talk a little bit about this issue. Like in a virtual watershed, how do you provide a tool for someone to move beyond this train wreck? You know, they're not working it out. So we built wood recruitment models to think about how wood falls into streams and accumulates there and decays and moves downstream, as Dan Miller was talking about. And these are all physically based models with the number of parameters that you need to drive it. And it's well documented in the literature how to make this calculation. There's multiple wood models out there. There's dozens of studies. You know, you need taper equations for the trees. You need a hill slope gradient. You need to know the vegetation, tree height, and so on. So I'm going to show some results from this kind of analysis. And the management scenarios is that this is the stream. So one side of the stream is never touched, even if it's a second growth forest, it's just not touched. And then the other side is split into two sections. One can be a 10-meter buffer or not. You can have a buffer or not, and then you just thin. You can either thin both or just the back stand, or you can do the same thing on this one, but you can thin and tip. What do I mean by tipping? So instead of taking all the trees to the mill, so a heavy thin might take 50% of the stems, you take some percentage of them and you drop them directionally into the stream. And that's called tipping. So the question was, from NOAA's perspective, hey, you guys want to thin? How many trees are we going to lose in the stream? And if you're going to lose streams, how many do you have to put it back in to mitigate? So this is the forest growth predictions and thinning. So the timber companies and the federal government, they project tree growth using forest growth models that go out maybe a century. So they take the current stand condition and they inform that model and they turn it on, and it starts producing every year. It tells you how many trees are living, how fast they're growing, and what's dying. And so this is 100-year on the x-axis, and this is live trees per hectare on both sides. And this is live trees in this column, and dead trees in this column. This is no treatment. That's if you did nothing. This is a single entry thin. It was entered in 2015. This is a double entry thin. It was entered in 2015 and then again in 2040. And this just shows you the number of trees that are left. And so it's a huge difference if you can see these axes. And particularly if you're looking at the dead trees, because the dead trees are what's going to provide the wood into the stream that makes it ecologically beneficial. But if you thin heavily from below, they call it from below, which means you take the smallest trees first, you're basically reducing or eliminating mortality recruitment. I mean, that's how trees, they die and they fall in. There's bank erosion recruitment, but that's not in this particular simulation. And you end up with no trees falling in if you do a heavy thin. And so NOAA Fisheries comes and says, no game, right? You do a heavy thin, we're going to lack wood. And the forester will say, well, just give us a century, and these trees will be bigger. And when they fall in, they'll be beneficial. But that doesn't win the day. So what you can do with these simulation models in the virtual watershed is you can look at how much wood would accumulate in the stream based on not thinning or thinning with tipping. And so the dark black line is the no treatment. So that's the target, right? That's the current target. It goes out 100 years, and the thinning is this light gray line. And the regulatory agency sees this, and that's it, game over, because you can see that you're losing wood. And they say wood equals good habitat in these low gradient coho streams. If you don't match it, you don't have a game. So then what we do is we say, well, we have mitigation, which is tipping. We can tip 5%. So in other words, instead of taking all the wood to the mill, 5% stays on the ground into the stream, or 10 or 15 or 20%. And we wanted to see what the effect was. And so for the first 30 or 40 years, if you tipped, you had way more wood in than if you didn't touch the stand at all. And then if you put a 10-meter buffer on that stream, though, and don't touch it, then the entire effectiveness of tipping goes away, because your first 10 meters are untouched zone and you can't get in there. And so you don't have much of an impact, but you don't have much of a beneficial effect either. And these streams have very low wood because they've been splash dammed, and they'd like to have some more wood in them as a restoration target. So this is if you have a double entry thin on only one side of the stream, and you have twice the positive benefit effect. So these dashed lines, that means you're tipping at 5%, 10%, 15, and 20%. So now you're after more than a half century, you've got more wood in the stream. And then after that, though, you start losing it from what would be the natural condition with an untreated stand. If you put a 10-meter buffer on it, the whole comparison kind of shrinks. Everything gets about the same. So these are the values. So this is a single entry thin. This is cubic meters per 100 meters. So you're going to lose 33% of your wood in the stream, or even 42% if you just thin it. If you put a buffer on it and just thin it, then you're still losing 10 and 7 and 10. And then if you start thinning and tipping, you can see that you start gaining. At 15 to 20%, you're gaining 1 to 6%, and over here you're starting to gain at 10% to 20%, more than what you'd have under natural, untreated conditions. The interesting thing is I mentioned that the treatment was only on one side of the stream. So what if you treated both sides at the same time with the same activity? It's a huge effect, right? So you double both losses and you double gains. So if you double the loss, it's a big hit on the stream wood and on the habitat. But if you tip on both sides at the same time, you can put up to 50% more wood in the stream. Now, as you know, putting wood in the stream is a restoration activity. At least it is in the lower 48. It's a big deal. The whole industry has borne up from putting wood in streams. And so this is a restoration technique that's tied to a thinning and timber harvest scenario. So this is designed to get the people in NOAA fisheries to talk to the Forest Service and private sector to come together in ways to think about more creative solutions in riparian zones that would include benefits to the fish habitat. We can think about wood recoupment as restoration. So that last thing was just about managing individual reaches. But there are people who so certain federal agencies and state agencies that say, I've got listed species here. How can I think about adding wood to the stream or improving riparian conditions? So we have data on tree sizes at the 30-meter grid cell scale throughout Northwest US. And we take that and we put that in our models in the virtual watershed. So this is current in-stream wood recruitment by size class. So we can calculate the wood recruitment by different size classes. And this is 75 to 100 centimeter diameter, 50 to 75, 25 to 50, and 10 to 25. And these axes, these legends are all the same except for the last legend break. And basically what it's showing you here is that the dark colors mean there's very little big wood in the stream. It's not a surprise. Most of that watershed is either private sector forestry, where they've logged it heavily, including before there were riparian zone prescriptions, and also lots of agriculture. And so where they just cut the trees and they never put them back. So you've got this huge pattern where most of the wood is small. So people can look at this map and say, well, where do I want to actually put wood in the stream? Or where do I want to grow big, giant riparian zones with big trees? So the other tool in the riparian zone toolbox in the virtual watershed in NetMap is thermal refugia. Again, there's two different watershed councils here that think about this stuff. Like, where should I plant more trees in the riparian zones? Where should I put wood in? Is it just randomly, or should I add other considerations? Like, well, why don't you put it where there's going to be cold water? because the fish, if it's warming climate, we want to know where there's going to be thermal refugia, and that's where you put your $50,000 log jams, or you're going to put side channels on your floodplains. And so we came up with a way to look at thermal refugia, and this is simply a map that looks at the thermal loading with current shade. And some areas are really warm. This is the warmer colors, means it's definitely hotter in the model, and the cooler is more topography and more vegetation that's causing a greater potential for cooler stream temperatures. And you can aggregate these values downstream or sum them up downstream, as Dan was talking about with the virtual watershed, and you get tributary scale predictions. So which tributaries are most likely to provide cool water, if you want to think at that scale. Some people like thinking at the entire tributary scale. The other thing is, once you have the tributary scale, it's simple to ask, where do warm temperature streams intersect cold temperature streams from a thermal loading point of view? And so now you just look at all the tributary confluences, where the warmer color streams are intersecting cooler color streams. That's a warm water spot. Do you want to spend your money there? Now, certainly you'd want to validate this prediction, but do you want to put money in restoration there? Or do you want to go find places where the topography and vegetation is set up to provide cool water at these junctions? And maybe there you want to put your money in. And finally, that the valley floor, the floodplain width and how it varies downstream is sources of cool water. So when there's a wide floodplain being necked down into a canyon, you get upwelling. So you got all this hyphoric flow coming up. And the opposite is true in the reverse. But so now we can say, well, where are the floodplains being constricted? And then these would be areas where you'd expect upwelling hyphoric flow. And lastly, and only one slide, it's like you can add erosional processes to the mix if you want. And as people have been saying, the LiDAR in Alberta is amazing, which it is. And you can create examples or create maps of erosion potential. So the last little topic I'll get into quickly is delineating the variable width riparian zone to the Simonette. Now, we've gone through a lot of these, but we're just going to include shade, wood, floodplains, and wet soils through WAM. And we're going to add them all together. The conceptual framework is pretty simple, right? Is that we get the different maps for the floodplains, the wood recruitment, the wet areas, and the shade thermal energy. They vary, right? All these places vary from reach to reach, and you can now create these zones, and you can have a composite zone, actually that's what we're after, and you can have left-right distinction. Like we talked about, it depends on which side of the stream you are on how much thermal energy is coming in. So left-right channel distinction is important. And then from a management point of view, each riparian process, the protection level can be adjusted in the tool in NetMap. Do you want to protect 100% of the wood or 100% of the shade or only 80%? You just turn the dial. Or do you want to have a limit on the lateral extent? Because these wet areas can go out hundreds and hundreds of meters, and even a floodplain can go out hundreds of meters. Do you want a regulated riparian zone that wide? Or is that going to start impinging on people's, in the US, it's like property rights, or is it going to have other implications? So the tool allows you just to set those dials. And you end up with these maps. So I'll just quickly walk you through them. So this is the wet areas riparian delineation zone, which has a lateral limit of 30 meters. That was arbitrarily decided among the study team. Could be anything. It could be 50, could be 10, could be unlimited. But then you get these giant zones. Same thing with floodplains. It was also limited to 30 meters. There's a wood recruitment that's tied to tree height in the data that was provided to us. And then you combine them all. As I mentioned, the conceptual zone, you just put them all together. And then you end up with the combined zone, but then when you're in the combined zone, you can say, and you can look at this map and say, what is controlling my riparian zone at any particular location? Is it the wet areas? Is it the wood recruitment? I mean, you could have areas with no trees, so there's no wood recruitment to worry about, there's no shade to worry about, but the wet areas drive it. So that's pretty key. And then, so you can see how some areas wood recruitment controls it, some areas floodplain control it, and so on. And so they end up with this map, which is just, this is the stream reach map. This is the WAM stream layer. So all this is the WAM stream layer that we imprinted on in NetMap. And you end up with this variable width zone. And you can see it ranges from about 10 meters to about 35 meters. And it has left-right distinction that you cannot see on this map. But you could actually create a map that has left channel side and right channel side, and it would be different. So this indicates how variable the world is in terms of riparian delineation.